Hello friends, memory is one of the most important components in the computer system, and also memory is one of the most important topic for your COA course. In this lecture, we'll discuss about the organization of memory. Basically, we'll see how to organize random access memory in our computer system. And also, we'll see a new type of memory which is cache memory. We'll discuss in this lecture what is cache memory, what is cache hit, what is cache miss, and all the basic things about cache we'll try to discuss in this video. So let's start the video. So before we jump for the actual topic of discussion, which is RAM and cache memory, let's have a quick revision. Quick revision of what? Quick revision of some of the basic things which we already discussed in our initial videos or initial lectures. What are those? We know in our processor we have many special purpose registers. Out of all, there is a special purpose register known as MAR. The full form is memory address register. This is the register where we store the addresses, or this is the register which deals with the memory addresses whenever you execute any program. And similarly, we have MDR, memory data register. So whenever you execute any program, if you need to transfer any data from memory to register or register to main memory, this MDR or this special purpose register helps you to do the things we have already discussed, right? Now, what is new in this slide? If this MAR is k bits long, means if your size of MAR is k bits and MDR is n bit long, and MDR, the size of MDR is n bit, then memory will contain up to 2 to the power k addressable locations. Means if the length of your MAR is k, then you have to understand that there are 2 to the power k different locations in your main memory that can be accessed by your processor. Fine. And similarly, if your MDR is of n bit length, then we will say that the data bus length is n, or the word length is n bits. Means each n bits will form one particular word. Fine. Now, one measure we know we have address bus to communicate with MAR and the memory. We have data bus to communicate with MDR and memory. Similarly, we have control bus or control line also, right? What is the major functionality of control lines? To send the control signals. Now, whenever we talk about memory operations, then what are the important signals your processor can send? Number one, it can send a signal that I want to read something from a particular location. It can send W, so that it will send a request to write something on a particular location. Or MFC. MFC is nothing but memory function complete. It's kind of acknowledgement. Whenever the task which processor was requested to memory is performed successfully, or everything is performed, then your processor will send a signal to your main memory that now my task is complete. You may release your location to you may release your data to some other purpose. Fine. It's kind of acknowledgement only, MFC, memory function complete. Now, some of the terminologies you have to remember. In this lecture or in our next 2 to 3 lectures, we will use this terminology, so you have to remember those. First one is block transfer. Whenever we say block transfer, means a collection of words I will send together. It's not bit by bit I will transfer. Understood that? Block transfer means a collection of words I will transfer at the same time. What is memory access time? The time that elapses between the initiation of an operation to transfer a word of data and the completion of that operation. Means memory access time is nothing but whenever you need something from your main memory, you started the request, and until you finish your execution, the total time from start to end, whatever total time you have taken, is nothing but memory access time. What is memory cycle time? Suppose you have two different operations to perform with your memory. So you have started one operation, after that you will start the second one. Now, if there is any gap between the first instruction and the second instruction, means you have completed the first instruction, now you are ready to execute the second one. If there is any delay in between that delay is known as memory cycle time. Fine, I hope you understood. Now we will see a block diagram of RAM or random access memory arrangement. We know repeatedly, we told many times that whenever we talk about memory, my main memory or memory is nothing but collection of n number of small cells, and each cell can contain one bit. We have already discussed this thing, right? So this is how your main memory looks like. How? So I will have different words, word 0, word 1, like this. I will have n number of words, and in each word I will have some bits, small cells which will contain one bit. So one bit like this. Fine. Now to choose any particular word, I use a decoder so that I can choose any one of the word. Once I get a cell, once I get the location, now what to do with this data? Shall I read or write or something else? To decide that, all the bits are connected with one CS, chip select, a small hardware. Through this, your processor will send the signal what to do, read, write or something else. Understood that? Now we'll see one example and we'll try to explain this block diagram with respect to the example. It will be more clear to you. What is the example? The arrangement of memory of 16 words. This is the arrangement. Totally you have 16 words in your main memory of 8 bits each. Means in each word you have 8 bits. You know word, right? Word is nothing but collection of bits. Now how many bits? 8 bits here in this question. 8 bits equals to one word. How many such words are there? 16. Now can you arrange this? Can you draw the block diagram for this arrangement? Yes. This is the block diagram for this question only. What do we have? 16 words. So word 0 to word 15. First you draw all the words. Now to choose any one of these words, since you have 16 different words, you have to use 4 to 16 decoder. So that if it is 0 0 0 0, you will go here 0 0 0 1 next, and 1 1 1 1 last one. We know that. Fine. Now this side I already told you, since 8 bits are there in each word, so B0 to B7, total 8 different small blocks or small cells will be there containing one bits, B0 to B7. Fine. And as I told you, chip select will be there for any arrangement, and these connections will be there for any kind of arrangement with the chip select for all the bits. Fine. Now in exam you may get a question. Block diagram is fine, it's very to draw, you can draw. The question is how many external points you need, how many external connections you need to complete this execution, to complete this block diagram. How many external connections you need? Now I'll make it very simple. Just pay attention, don't think much. If you are asked to finalize or if you are asked to tell how many total external connections are required, just pay attention how to calculate. Total number of external connections is nothing but, first you see what is the input to your decoder, how many input lines you need, note it down. For this example I have 16 different words, so I need 4 input lines. So these 4 are external lines. 4 plus, next important thing, you check how many bits are there in each word. For each word I have one connection. For this example I have 8 bits in one word, that means 8 connections will be there. So 8 plus 4, 13. Now for all arrangement, for any type of memory arrangement, 2 lines, 2 external connections are necessary to connect with this CS or chip select. So 4 plus 8 plus 2. This 2 is common for any arrangement. Fine. Only changes will be in the number of input lines to the decoder and number of bits in the word. It will be mentioned in the question. Other than that, this chip select lines equals to 2 is fixed. And also for power connection or ground connection, you need 2 connections. That is also fixed for any kind of block diagram. So total how many connections you will say? 4 plus 8 plus 2 plus 2. That is the total count. 4 plus 8 plus 2 plus 2. Fine. Now if I ask you the next question, if I have 1K memory cells and the arrangement is 128 into 8, then how many external connections will be there? Can you think it? Yes, you are correct. So now what we will do? We know that there are 128 different words are there. 128 into 8 means 128 words are there, and in each word I have 8 bits. So how many external connections I will have? So for 16 different words I need 4 to 16 decoder. I need 4 input lines. 2 to the power 4 equals to 16. Now for 128, how many input lines I need? 2 to the power 7 equals to 128, right? So I need 7 input lines to the decoder so that I can select any one of the 128 words. So 7 for input lines. I have 8 bits, so 7 plus 8, 15 plus 2 plus 2. Plus 2 for chip select, plus 2 for ground connection. That's it. 7 plus 8 plus 2 plus 2. Similarly, if I ask you how many external lines will be necessary to draw this one, 1k into 1 means I have total number of words equals to 1k, 1024, and total in each word how many beats are there? Only one. Then how many total lines will be there? Can you tell me? Yes. How many input lines will be necessary to get any one of these 1k words? 10 bits, right? 2 to the power 10 equals to 1024. So 10 bits to get any one of the word, and for bits I need only one connection because only one word is there. One bit is there in each word, right? So 10 plus 1, 11 plus 2 plus 2. Fine? 15. So this is the arrangement of 1k into 1. So I have total 1k different words, and each word I have one bit. Fine? I hope you understood. So that was the basic arrangement of your random access memory or main memory. Now we have gone through, we heard many types of memories, right? We heard about secondary storage, we heard about main memory, we heard about cache, we heard about registers. So this is the memory hierarchy. Means if you see the size, then registers are the smallest memory you have. Primary cache, we'll come to that cache, don't worry. Cache also you have two types, L1 and L2. So L1 is somehow bigger than register but still very small. Secondary cache is again small but bigger than this. So this way is increasing the sizes. Fine. If you talk about the speed or how fast it can be executed, then you go to the reverse way. Secondary storage or secondary disk is the slowest memory you have. Main memory is somehow faster. Secondary cache more faster, fastest. Fine. Now if you talk about cost, how expensive it is, this is the most cheaper one, then a little expensive, more expensive, that the most expensive. Fine. Now out of all these memories, main memory, I already discussed how to design the main memory and all. Now we'll start about cache memory, one of the most important topic for your exam and for your competitive exams. Cache memory. So first question is, what is cache memory? Yes, your answer is correct. Cache memory is nothing but a temporary memory which is placed in between processor and main memory so that it can store the information which is repeatedly used or most recently used. You understood that? Means, say you perform something A equals to B plus C. Fine. Again after 5 minutes you need the same operation, A equals to 5 plus 2 or whatever you have done. Same operation you need again after 5 minutes. Now instead of going back to memory, perform the operation again and again, what we can do is, since first operation is already done successfully, the information I can store to cache memory so that next time if processor want to access the same thing, then it can get from the cache memory. And we know cache is the fastest memory, faster memory than main memory, so things will be more faster. But this memory is very small and very temporary. It's not that we can store everything from main memory. That is not possible. Fine. Now about cache memory, we'll see more in a more detailed way in this diagram. So the first thing, if I ask you what is word, now everyone will say we know what is word. Word is nothing but collection of bits. Now whenever you transfer anything from main memory to your processor or main memory to cache, it's not possible to send bit by bit, right? It's not feasible that you will send one bit at a time, take one bit, next bit. It's not feasible, or it's not a good idea. Then what next? Sir, we can send word by word. Maybe at a time I can send one word. Still, word by word also, your main memory has many words, right? So how many times you will send word by word? And we know to store some information, I need more number of words. One word is not sufficient for that, right? I need a group of words. For that, what we do is, we never transfer anything bit-wise or word-wise. Rather than that, we make a group of words together and we call this as block. So one block is equal to some collection of words. How many? It depends on the application. For this example, this is the main memory. If you see, I have total 128 different words, word 0 to 127. So total 128 words I have in my main memory. But what I did, I have partitioned these all words into some blocks. So in each block I have 4 words. So totally I have 32 different memory blocks. You understood that? Similarly in cache also same concept is used. We don't take anything bitwise or wordwise. Here also we make some blocks, cache blocks. And the concept is exactly same. Cache block is again nothing but collection of some cache words. Fine. But we know our cache memory is very smaller. So what we do is we cannot store everything at a time. So rather than that, some of the information from main memory I store to cache temporarily. You understood that? Now logically you should understand that if I want to store something from main memory to cache, then this is obvious that this block size, memory block size, should be equal to cache block size. Otherwise how you will store, right? So if you see this cache diagram, then I have only how many blocks? 4 blocks. So I can store only 4 blocks from my main memory, and this block size of cache is exactly same with the cache size of main memory. You understood that? I think that's clear. Fine. Now suppose your processor was asking something from your cache. So whenever your processor needs something, remember that it will first ask to your cache. If your cache can return it, fine. Otherwise your cache will ask it to main memory. It's like someone is there in between. I'm not directly asking my class teacher for the attendance. Rather than that, what I'm doing, I'm asking my CR. That CR, please give me the information about the last class, whether I was present or absent. CR will say, I don't know, I have to. If CR knows, then he will directly say, yes, you were marked as absent or present, I saw. Otherwise, CR will go and ask teacher, sir, whether he was absent or present in that day. Then there are multiple ways. Teacher directly can tell me also. Teacher will send the information to CR. CR will send this to me. There are 2 different ways. We'll discuss those things. Now, whenever your processor is asking something from your cache, if the particular data or information is present in cache, it may be, it may not be, because I don't have a very large cache, right? We don't know. If it is there by chance, then we call it as cache hit. Cache hit means the data which was requested by processor to cache is present or available. Fine. Cache hit sounds very interesting. Now, if processor want to read something, no issue. It will get the data, it will read, and then okay, it will say, okay, I have done with my work. Fine. It is very faster. Now the problem is with write operation. So your cache is holding something temporarily from main memory, say a equals to 7, your cache is holding, which was actually there in main memory, a equals to 7. Temporarily your cache is holding, and processor want to modify it. Processor want to make it from a equals to 7 to a equals to 10. There is a problem, because we have to update this value to main memory as well. Otherwise there will be a difficult situation. So how to write the same thing to your processor also, main memory also, whenever you are writing something to cache? We have 2 different protocols. First protocol is write through protocol. Using this protocol, whatever changes you are making to cache, you can make the same changes in the main memory as well. How it deals with? See, suppose this is my main memory, where this block has a equals to 5. This is the information, a equals to 5. And same information I have copied to my cache also, a equals to 5. And here I have b equals to 3. Same information I kept here, b equals to 3. No problem. Now processor want to read a equals to 5. If it want to read, then there is no issue. Suppose processor is asking for some change, means he want to make a equals to 6. From a equals to 5, he want to make a equals to 6. Then what you will do? In write through, it says whenever you are making some changes in cache, immediately you go back to your main memory to the same location and you do the same change there also. You understood that? Whatever modifications you are doing here, immediately you do the same modification to the main memory, so that the data will be updated, because in main memory you should have the updated value, right? Fine. So initially I made it from a equals to 5 to a equals to 6. This request went to here, and here also I have a equals to 6. Next I want to access b, I want to change in b equals to 3 to 8 I want to make. Similarly I will go back to my main memory and I will make b 3 equals to 8. Again in the third clock pulse, or after some time, I came back to the same block A, and again I want to make it from 6 to 2. So I made the change here, and this change will be again updated to your main memory. a equals to 2. So this is how you write through protocol works. You understood that? Now can you tell me any disadvantage of this algorithm or approach? Yes. Number one, see, whenever I have written something my cache, say after that immediately I have to write the same thing or modify the same thing in the main memory. Means I have to wait until and unless this was not updated, I cannot go for the next instruction or next information. So processor need to wait some time because the write operation is twice now. You are doing once here, then only your processor can execute the next information. First disadvantage. Second disadvantage is, see, here I made some changes here, a equals to 5. After some time again I made some changes, a equals to 6, again a equals to 2, maybe again I am changing to 5. So what is our main goal? Our main target is my main memory should have the updated value, not every values. What is the updated value? A equals to 2, or maybe after some time I made it to a equals to 7. So my target is this, in this location I shall have a equals to 7 or 9, whatever the updated value is. Not every information I want. You understood that, right? Every time I am modifying here, why I am modifying here immediately? Better what I can do, I can wait and I can see. I can wait for the updated value. Who knows, after some time you are again changing this. So I'll wait for the updated value. Once everything is done, I can send it to the main memory location. So this is one more drawback here. From these issues, we have the next protocol, which is write back protocol. So in this write back protocol, what we do is we never change immediately to my main memory. Whenever you are doing some changes in cache, immediately we won't modify it to the main memory location. How it works? Let's see. Suppose I have a equals to 5 somewhere in the main memory and I have copied the same thing to my cache, a equals to 5. And your processor want to modify this one, a equals to 5. So once you modify it, say you made it to 6, from 5 you made equals to a equals to 6. Once you modify this, what I will do is I have a dedicated flag bit for each block in the cache. Fine. One flag bit is reserved for each block of my cache. This bit can be 1 or 0. 1 means you have done some modification. 0 means no modification was done. So now what will happen? How many times, no matter how many times you are modifying this one, this will remain 1 only. Fine. Next you will check the other blocks whether you have to modify something or not. Here also maybe you are modifying something. So this flag bit is also known as dirty bit. You have to remember that. This dirty bit or flag bit is 1. Here you are just reading, you are not doing any modification, so dirty bit is 0. Here also you have done with some reading operations, so dirty bit is 0. So once all the operations are done, your processor is done with all the operations. Finally, now your main memory will check where are the ones and where are the zeros. If there is any 1, then main memory will ask to send the updated value. If it is 0, then no changes. You understood that? Like this, you are saving your time, right? We are not modifying immediately. Rather than that, we are waiting for till the end of the program. And once everything is done, then only I will modify it. So what is the updated value? 2. So only 2 will be copied here, nothing else. So I hope you understood these protocols, write back and write through. So this was about cache hit. Now, if there is cache miss, what to do? In cache hit, we saw if there is reading operation, no problem. If there is writing operation, we have some issues. And we have discussed 2 protocols how to do write operations, right? Now if there is cache miss, what to do? Means whatever you are asking in your main memory, whatever you are asking from your cache, it's not there. So we call it as cache miss. So what we will do if it is a cache miss? There are 2 possibilities. One, if it is a cache miss, your cache memory will look for the data in main memory. Once the data is found, then your cache memory will forward the data to processor. And second thing is your main memory directly can send the data to processor. There are 2 options, right? So the first option, where what you are doing, so whenever you are requesting something from your cache, it's not there, your cache is requesting to main memory, then main memory can directly send to processor, same time it will send to your cache also. If you are doing this, then this is called write back protocol. You are using write back protocol, load back protocol, not write back, load back protocol. But if your main memory is not sending, rather than that your main memory is sending the information to cache is forwarding the data to processor, then we call it as load through protocol. Fine. So in our next video, we'll discuss some more concept about cache memory. That's it for this video. Thank you for watching.